to, that might have questions on it? Yep.
Can you check question 4?
Question 4? Sure. Yeah, that's one of the ones we did, and it's okay. We'll do that. We can do it again. I mean, that's not a problem. This one actually, I think every single class has asked about it. So it's a good problem. It's a good problem to look at. It says two functions are defined below, and we want to find the domain of the composition f of g. So we have to understand this composition and how we can, kind of work with it. So f of g of x can be written as f with g of x plugged into it. Okay. So if you want to evaluate this function, you can start by plugging things into g, as your first step. So what can we plug into g? What would be a good number to start with that we can plug into g? If we look at the domain of g, we can start with, let's say 0, and it's right there in the top. So 0 is definitely a value that we can plug into g, right? So let's try plugging in 0 into f of g. F of g of 0 is f of g of 0. And so can somebody tell me what g of 0 is? 4. So f of g of 0 is 4, and we can see that because of this arrow right there. And so now this just becomes f of 4. What is f of 4? F of 4 is 4. Yeah. Good. So this becomes 4. And so that means that f of g of 0 is equal to 4. And that means that the domain of f of g includes 0. We were able to plug in 0 into f of g and get an output value. And then the output value that we got is 4. So 4 should be part of the range. So far we've determined that 0 is part of the domain. 4 is part of the range. Let's try another one. Let me switch colors here. F of g of 1. So that can be written as f of g of 1. What is g of 1? G of 1 is 1. We can see that right there. So this then becomes f of 1. What is f of 1? Yeah. F of 1 is not defined. There is no 1 in the domain of f. So that tells us that we cannot plug in 1 into f of g and get an output value. So that means that 1 is not part of the domain of f of g. Okay. And so we just go through and check them all and see which of the values we can plug into the function f of g and get an output value for. And then all the inputs that we were able to plug in and get an output, we put all those inputs into the domain. All the outputs that we get from those inputs, we put them in the range. Okay. So, yeah. Is that clear? Yeah. Okay. Since we did do it in the previous class, I'll leave it there and then you can figure out the rest of it. The answers are at the back of this too. So you can scroll all the way to the back and check your answers. And then if, for some reason you can't figure it out, you can watch the video from my previous class. And we did it in there. You can see the whole solution. Yes. Well, we're looking at both. So let's take a look at one more of these values. F of g of 2. It's just the way that f of g is defined. F of g is defined as you apply the function f to g of 2. So can you tell me what g of 2 is? 0. So g of 2 is 0. And so we replace g of 2 with 0. And notice now we have to find f of 0 if it exists. So what is f of 0? f of 0 is 5. So it existed both times, like it worked. G of 2 we could find, f of 0 we could find. That means that f of g of 2 is defined and it's equal to 5. So 2 now belongs in the domain of f of g, and 5 is part of the range of f of g. Okay. All right. And then you can continue with 7, 8, and 9. Yes.
To ask you to retrieve all of them for ones that you could get.
Yes. So yeah. So you want to keep going through 7, 8, and 9, and then figure out which of those are defined that give you output values and which of them are not. You know, like 1 we did not put in the domain because we could not get an output value when we plugged in 1 into f of g. 5, that was the number that we ended up with when we plugged in 2. Just now we plugged in 2, and the output value was 5. And so for the domain remember is the inputs and the range is the outputs. So 2 belongs in the domain and 5 belongs in the range. All right, very good. All right, what other questions? And we can go through just, feel free to take a look at, open this up on your computer, and you can kind of swipe through and see which ones look challenging. I am going to try to do problems, maybe that haven't been done so far. But if you have one and you choose one that's already been done, that's okay. We'll just do it. That's no problem. So while you're looking through there, maybe I'll take a look at number 7. We didn't talk about division. So here it says divide. We're dividing 2 polynomials. Your answer should give the quotient and the remainder. Okay, so we're going to do some long division here. Did everybody do long division on Alex? Yeah. Okay, good. Yeah, everybody should have seen this. If you didn't, maybe you didn't get far enough, or not sure if it. Yeah. So how do we do this? It's very similar to dividing by a number. I'm gonna actually do a real quick problem before 7. I'm gonna divide this into 135. Or actually, you know what? I'll do 1,352. Okay, so how would we do this? We ask ourselves, how many times does 7 go into 1? And it does not. How many 7s are there in 1? 0. So we multiply 0 by 7, that's 0. And then we subtract these two numbers, we get 1, and we bring down the next value. How many times does 7 go into 13? There's one complete 7 in 13. 1 times 7, we multiply and we get 7. Oops. And then what do? We subtract these two values, right? 13 minus 7 is 6. We bring down a 5. How many times what do we have to multiply by 7 to get 65, or as close as we can get to 65? What is it? 9, yeah, 9. If we multiply 9 by 7, we get 63. That's as close as we can get to 65 without going over. And then this 63 is positive, but we subtract it. And so we get 2. Bring down the next 2. What do we have to multiply by 7 to get as close as we can to 21? To 22. That'd be 3, which is 21. 3 times 7 is 21. We subtract, we get 1. And now we've brought down all of the values. That is our remainder. So our answer is that 1,352 divided by 7 is equal to, we can say 193 with a remainder of 1. Okay. And so this process of dividing these numbers here is very similar to the polynomial division that we're about to do. So let's set this up. 6x minus 1 dividing into 12x cubed plus 4x squared minus 7x minus 2. So the question that we ask is, what do we have to multiply 6x by to get as close as we can to 12x cubed? What can we multiply by 6x? Yep,
Squared.
2x squared, 2x squared, yes, very good. If we multiply 2x squared by this 6x, that gives us 12x cubed. Now, in this case, there are two terms, so we'll multiply to both of those to the -1. 2x squared times a -1 is -2x squared. And then just like before, we ended up subtracting these numbers. We're going to subtract these terms. And that amounts to switching their signs, because if you subtract a positive term, you just subtract it. If you subtract a negative term, then it would change to addition. And so a term cancels here. 4x squared plus 2x squared is 6x squared, and we bring down the next term. Okay. Next question. What do we have to multiply 6x by to get 6x squared? Say again? Not 6x. We're going to multiply 6x and we want to get 6x squared. Yeah, just 1x. Yeah. So plus 1x. 1x times 6x is 6x squared. 1x times a -1 is -1x. We switch the signs of these terms. We subtract them, just like we did in the regular division. And we end up getting that these terms cancel. -7x plus 1x is -6x. And we bring down the -2. And now what do we multiply 6x by to get a -6x? Say again? Not 1, -1. Yeah. -1 times 6x is -6x. -1 times -1 is +1. And then we subtract these terms. We subtract, so that would change the signs. I'm just going to put a minus sign above that one. -6x plus 6x cancel, and -2 minus 1 is -3. So our quotient is 2x squared plus x minus 1. Our remainder is -3. So kind of cool. The polynomial division works a lot like regular division. And there's a reason for that. We can get into that if we want to. All right. What else? What other questions do we want to see? Ooh, this is a good one. Let's see, maybe we can do this one here, the next one. It says below is the graph of a polynomial function with real coefficients. All local extrema of the function are shown in the graph. Okay. Over which intervals is the function increasing? Can somebody tell us which intervals over, give us one of the intervals over which the function is increasing? -5 to -2. That's this interval here. Yeah, the function's increasing there. Good. What's another one? 2 to 5. 2 to 5. Yeah, it looks like the function's increasing there. Very good. 8 to infinity. It looks like the function is increasing there. Yep. Very good. Everywhere else, it looks like it's decreasing. So that's it. Nice. At which values of x does the function have local maxima? If there's more than one value, separate it with a comma. What's the value of x at which we have a local maximum? -2 and like that. Yeah. So we want to be careful. Here we just want the x value. So -2 is correct. Yeah, it's not asking us for the y value because the y value is kind of approximate. It's like 2.75 or something like that. I'm not too sure what value that is. But yeah. So -2, that's the x value. What's another x value that we have a local maximum at 5? Yeah, right there. The x value. The x value. Okay, very good. What is the sign of the function's leading coefficient? What is the sign of the function's leading coefficient? Positive? How do you know that? Good, nice. You know that it's, well, yeah, for sure. The ends are pointing in the same direction. They're pointing up, so it's even degree. And they're pointing up, so that'd be positive. Very good. And really, you only have to look at one end, the right-hand side. If it's pointing up, it's positive. If it's pointing down, it's negative. Whether the left-hand side, I mean, that's more information, so that's good. You know, that's even better. But yeah, even if they only showed us, you know, 1/2 of this graph, we could still determine that. Okay. And then the last part here, which of the following is a possibility for the degree of the function? Choose all that apply. What's that? 6 and 8. All right, and I'm going to need you to refresh my memory on why those two are the.
I remember see how many times it comes up. So 1, 2, 3, 4, 5, 6. So maybe 6 and 5.
Okay, changes direction. 1,
Um,
2, 3, 4, 5, and 6. Okay, good. Yeah, the number of yeah. Okay, yeah, very good. And then we know it's even for sure, so we definitely cannot be 7, 9, or 5. Yeah, and if you think about it, I mean, that works with like the function f of x equals x squared. It looks like that. It's going down 1 and then up, you know, that's 2. So, all right, very good. Nice. All right. What other questions? Oh, we can just go through. Yeah. Oh, yeah. 4? Yeah, so it can't be 4 because there's a couple of reasons. Let's see, which one can we give? A 4th degree polynomial, or let me write it this way here. A 2nd degree polynomial, and I'll just write polynomial, can have at most 2 the degree minus 1 turning points. Okay. Like the x squared function is a 2nd degree polynomial. It can have at most 1 turning point where it turns around. And so if it was a 4th degree polynomial, that would mean that it has at most 3 turning points. But if we look at it, it turns around once, twice, 3 times, 4 times, 5 times. Right? The turning points are each of these maximums or minimums. Turns once, twice, 3 times, 4 times, 5 times. And so since it turns around 5 times, a 4th degree polynomial can have at most 3 turning points, which means this cannot be a 4th degree. Yeah. There's that reason, yeah. Yeah. Okay, does that satisfy? Okay, cool.
How come it's 8?
How come it's 8? Because let's see, it says which of the following is a possibility for the degree? Sometimes a polynomial might have some factors that repeat. So we might have a factor of like x minus 4 to the 3rd power. And it has, so there's only one intercept for, there's only one x-intercept for those 3 factors because the, because that factor repeats, yeah, only one x-intercept exists. And so it can be more than 6, but not less than, yeah, it can't be 4 because that's too little, but it could be potentially more, like 10 or 12. It can continue to go up.
Like, let's say the answer is 4.
What do you mean? Yeah. So if there were less turning points, yeah, you would choose values, you need to figure out what's which ones are too small, like 4 is too small, but you want to choose, every value that it can be larger, I guess. It can be, yeah. So if there were bigger values like 10 and 12 on here, you would choose those as well. Yeah. Yeah, we can eliminate smaller values because of this statement here. The more general statement is an nth degree polynomial can have at most n minus 1 turning points. So this one here, since it has 1, 2, 3, 4, 5 turning points, its degree is going to be at least 5 plus 1, at least 6. So that could be 6 or 8 or 10 or more. All right, very good. What else? Yes. 15. All right, let's take a look. 15. This is a good one. So, number 15. We're given a function, the square root of 5 minus x plus 4, and we're asked to find the domain of the inverse, and we're also going to find the inverse. Okay, so before we find the inverse, can somebody tell me how do we find the domain of the inverse? The range, right? The range of this function will be the domain of its inverse. So if you remember that relationship between inverse functions, so let's actually just sketch a graph of this thing. The square root of x looks like this. This one it has some stuff going on here where it's reflected about the y-axis, and it's shifted 5 units either to the left or right. But what we care about for the range is this right here, this plus 4. We know that means it's shifted up 4 units. And so can somebody tell me the range of f? What's the range of f? +4 to positive infinity. Yeah, so you have to know that for the square root function, the range is 0 to infinity, right? It starts right here at a y value of 0, at a height of 0, and then it starts to go up to infinity. So 0 to infinity, but this one got shifted up 4 units, so its range is 4 to infinity. So that's going to be the domain of f inverse. Notice we haven't even found the function f inverse yet, but we know its domain. Okay, that's something we know so far. Now let's go ahead and actually find the function. What were the steps in finding an inverse function? There were 4 steps. The first one was just to let f of x, just switch that with a y. The second step, switch x and y. Those 2 steps are usually pretty easy. The third step was to solve for y. So we'd solve for y by subtracting 4. You get x minus 4 equals the square root of 5 minus y. And then we would square both sides. So x minus 4 squared equals 5 minus y. Subtract 5 on both sides. So we get x minus 4 squared minus 5 equals the opposite of y. Divide by a -1. So I'll flip it around here. Y equals negative x minus 4 squared plus 5. And then the last step was to just replace y with f inverse of x. Few steps there, find the inverse. And we should be able to fairly accurately graph this if we wanted to, it's shifted to the 1, 2, 3, 4, right? 4 units and 1, 2, 3, 4, 5. 5 units up. So it would look something like this, something like this. Now, I'm actually making a mistake here. We know it's a parabola facing downward, but because of the domain, we said the domain of this is from 4 to infinity. So actually, I've made a mistake by including that half there. I need to delete that half there. And that is the inverse function. It's only half of a parabola. And of course, actually, I guess it should be because we said the other one is it's a square root function, which is half of a parabola on its side. When we reflect that about the line y equals x, we're going to get half of a parabola. All right, so which half of the parabola? Yeah, it's the right half, I guess, this time, from 4 to infinity. All right. Questions there? Nope. All right. All right. What other questions? There's a lot of good problems on here. Let's see. Oh, yeah. Uh-huh. Negative infinity to 5? Yeah, it's kind of just extra information, I guess. That right there, I would say, yeah, there's not really much to, there's nothing to do with it. You don't have to do anything with it. But if you notice, this is the domain of f. So can you tell me what the range of f inverse is? What's the range of this function that we just graphed? It's negative infinity to 5. So I mean, it matches up, I guess, what we should expect. The domain of that function f is the range of the function that we found, the inverse. So, and then we graphed it, those things match up, that's good. Yeah, but there's not really anything we need to do with it, I guess, no. All right, very good. How about, do we want to see number 16? This is finding the inverse function of a rational function. We didn't actually see this. This used to be in the worksheets, back a few years ago when I taught this class. At some point it got taken out. So do we want to see how to find the inverse of a rational function? Yeah. Let's see, it says find G inverse. So we're going to take the exact same steps. I'll start with step number 1 here, just to replace G of X with Y. This one is a little bit more challenging than the one we just did. Slightly, there's a trick that you need to use in order to be able to do this one. And then we said switch X and Y. So here there are multiple X's. They're both going to become Y's. So Y minus 7 over 9Y plus 2. Okay. And now we solve for Y, just like in the previous one. Now solving this for Y, we should probably multiply by the denominator, the least common denominator. And so we get 9xy plus 2x equals y minus 7. How do we solve for y when there's two y's? Combine them? Yeah, maybe we can try to combine them. So at least let's get those terms on the same side. Right, we'll have better luck trying to combine them if they're at least on the same side. So we have 9xy minus y equals negative 7 minus 2x. But those are not like terms, so we can't really combine them because one has an x and one doesn't. What's the alternative approach? Factor. This is what we saw in the logs. So that's part of the reason I wish this hadn't been taken out, because we would have seen this. But with the logs, you can't easily combine sometimes those logs. So you get all the ones that have the x on the same side or the y on the same side, and then you factor out that variable. and we can divide by that other factor. So y is equal to this. Did we see those on Alex in the homework? Yeah. Is there another way to do this problem? Or is that the main way that we used? Yeah, if you use that way, that method, that's good. Yeah. There's another approach, but it's kind of a cheating approach, so I won't give it out.
Is it memorizing?
Yeah, yeah. Okay, so that's what I was looking for to see if anybody noticed that. Yeah, these actually, yeah, they have a pattern, and I don't even know what the pattern is, but there's like a way to do it so that you just swap the numbers, change a couple signs, and then that's the right answer. Which, if you can notice that and do it, I guess, yeah, definitely a problem like this with a rational function, I won't put on the exam because we didn't see rational functions on the worksheet, so I won't go that far. But so you're safe to do it on Alex if you want to try that. All right. What else? Yes. 21. All right. Ooh. Okay, that one's nice. 21. So it says use the properties of logarithms to expand the following expression. Each logarithm should involve only one variable and should not have any radicals or exponents. You may assume that all variables are positive. Okay, so we want to get rid of any radicals or exponents. Okay, so yeah, the first thing that we could do is we have log of a quotient, a fraction, right? And there was a property that allows us to combine two logs, and we would divide the arguments. So how can we rewrite this? As our first step, I mean, you can do this in one step, but I'm going to take a couple steps to do it. As our first step, we can do log of the numerator minus log of the denominator. Because you know that you could combine those two logs again, divide the arguments to get that single log back. And then you start to notice, well, wasn't there a property that allowed us to bring exponents out to the front? Yeah. So we're going to bring that exponent out to the front. We don't want any radicals, so that square root, we can write it as an exponent of 1/2, right? And so, yeah, we can write this as 7 log of y minus, and here I'm actually going to split this up because this is x times z to the 3/2. So I can write this as minus log of x plus log of z to the 3/2. 3/2 because the radical became a 1/2, and the 1/2 times a 3 becomes 3/2. This negative does apply to both of these logs, so we want to try not to forget that. A lot of times people will split up a log and only apply the negative to the first one. I'm subtracting both the log of x and the z. And then at the same time, we can put this 3/2 out in the front. And so our answer will be 7 log of y minus log x minus 3/2 log of z. That is our answer there. Could we have done this in one step? Yeah, if you're comfortable enough to do these in one step, there's not really anything you need to do. Just know that anything that's in the numerator will have a positive log. So 7 log of y. Since both of these x and z are in the denominator, they should have negative logs. So minus log x, and then minus, make sure to write any exponents, in the front. So minus 3/2 log of z. Now you can do it in one step as well. All right. What else? Maybe got time for it, yeah. 22, sure. Yeah, this is a good one. This was nice. This could show up on your exam, the in-class portion, because we had something like this, yeah.
Just for Alex, like, parentheses that didn't have that, like for the lines.
Yeah, so right there, yeah, you do have to try to use like the same format that you see on the homework or on the practice exam. That's why the practice exam is opened up also. But that should have also been the case for the homework if you had done the same thing. So if you're wondering like maybe something's gonna get marked wrong or something, take a screenshot, and then after you get your scores or whatever, you can check your answers, and if something gets marked wrong, you can bring it up. Yeah, so that would be a good idea. Just take a little screenshot of it.
Yeah, so for the Alex portion of the exam, do you guys, the professors, like go back and look at it? Or do you guys just take what the exam gives us and put that in for our score?
Yeah, no, we don't really go back and look at it unless there's a big discrepancy between the in-class score. Like say you get like 10% on the in-class exam and you get 100% on the Alex one, then there's probably a line of code. David takes care of this, but that basically sets off an alarm and says, hey, there's something up here. And that's when we will go look at it. But otherwise, if you get 100% on both, okay, cool. That's nice. We don't look at the Alex one now. Yeah, part of the reason to have it on Alex is so that it just grades it real quick and then it's also you're being tested on the homework stuff that you have. Okay, so maybe we can go around and just somebody can tell us what the answer to part A is for this one.
A is 35.
35. Yeah, very good. We just multiply, right? The argument. So that was one of the properties of the logs. If you're adding two logs together, you multiply the arguments and combine them into one log. So log of 35. Very good. Okay. And then what about part B? What would the answer to part B be? If there was a 3 here, when we combine those two logs, since they're being subtracted, we would divide the arguments. That would give us 4/3, which is what we're looking for there. Yeah, good. And then the last one, part C, that would also be 3. Yes, because there was a property that said an exponent, we just use that property. The exponent can come out to the front of the log, but we can also reverse this and think what number raised to the -4th power would give me 1/81, and that would be 3. 3 to the -4th is 181. Another way to think of this, let's see. Yeah, you could say this is log base 5 of 81 to the -1st power. And then, yeah, it's kind of a roundabout way, I guess, to do it this way, but log base 5, 81 is 3 to the 4th power. And that's raised to the -1, so this is log base 5 of 3 to the -4th, and then that -4 can come out front. So this is -4 log base 5 of 3. Yeah, so the easiest way is just to say, okay, if I put this back up here, what number to the -4th gives me this right here, 1/81, and that's 3. Is that how you determined it? Or did you come up with it a different way? Okay. Okay, cool. Very good. All right. Any other questions that we want to look at? If not, we can stop there and oops.